Imagine you have a deck of cards, but they're all mixed up, just numbers. Can you arrange them into groups where every single group has the exact same number of cards? Today's problem is exactly that, X of a kind in a deck of cards. Take a moment, what would you do? Let's dive into what this problem asks. You're given a list of numbers like a deck of cards. For example, you might have a deck that looks like 1, 2, 3, 4, 4, 3, 2, 1. Our goal is to figure out if we can divide all these cards into groups, such that every single group has the exact same size. Let's call that size X. And there's a crucial condition. X must be at least 2, so we can't have groups of just one card. Every group must have 2 or more cards. If we can successfully make these groups, we return true. Otherwise, we return false. Let's look at our example. 1, 2, 3, 4, 4, 3, 2, 1. Here the number 1 appears twice. The number 2 appears twice. The number 3 appears twice. And the number 4 also appears twice. Since every single distinct card appears exactly 2 times, we can form groups of size 2. We'd have a group of 2 1s, a group of 2 2s, a group of 2 3s, and a group of 2 4s. Since we found such an X, which is 2, and it's greater than or equal to 2, our answer for this deck would be true. Now consider another example, a deck with just 1 1 1 2 2 2 2 2 2. Here, 1 appears 3 times and 2 appears 6 times. Can we find an X that works for both? If X is 3, we can make one group of 3 1s, but for the 2s we have 6 of them. Can 6 be perfectly divided by 3? Yes, 6 divided by 3 is 2, so we could make 2 groups of 3 2s. Since both 3 and 6 are perfectly divisible by 3, X equals 3 works. So for this deck, the answer is also true. What makes this tricky? We need to find a single asterisk group size X that works for all the different types of cards in our deck. It's not enough for some cards to form groups of size X. All asterisk cards must be able to form groups of size X. The constraints tell us the deck can have up to 10,000 cards, and each card's value is between 0 and 10,000. This means we need an efficient way to count cards and then check our grouping condition. The most straightforward, or brute force, way to approach this problem is to try every possible group size X and see if it works. What are the possible values for X? Well, X has to be at least 2 as per the problem statement. And the largest X could possibly be is the total number of cards in our deck. If we have 10 cards, maybe we can put all 10 cards into one giant group, so X would be 10. So we can start by checking X equals 2, then X equals 3, then X equals 4, all the way up to the total number of cards in the deck. But before we can check any X, we first need to know how many times each specific card appears in our deck. For example, if we have the deck 1 1 2 3 3 3, we need to know there are 2 1s, 1 2, and 3 3s. A great way to do this is to use a data structure called a dictionary or HashMap. We'd go through our deck card by card. For each card, if we've seen it before, we increase its count in our dictionary. If it's a new card, we add it to the dictionary with a count of 1. Once we have all these counts, we can begin our brute force check. We pick an X, say X equals 2. Then we go through every single card type in our dictionary. For the 1s, we have 2 of them. Is 2 perfectly divisible by our current X, which is 2? Yes, 2 divided by 2 is 1 with no remainder. So far, so good. Next, the 2s. We have 1 2. Is 1 perfectly divisible by 2? No, it has a remainder. So X equals 2 doesn't work for this deck. We then move on to the next possible X, say X equals 3. We'd repeat the process. Check if 2 1s can be grouped by 3, no. If 1 2 can be grouped by 3, no. If 3 3s can be grouped by 3, yes. Since it didn't work for the 1s or 2s, X equals 3 doesn't work either. We would continue this for every possible X until we find one that works for all asterisk card counts, or we run out of X values to check. This approach is correct, but it can be slow. Counting the cards takes time proportional to the number of cards in the deck. Then we have a loop that checks every possible X, and inside that loop, we iterate through all the unique card types. In the worst case, if all cards are unique, there could be as many unique card types as there are cards. This means our time complexity could be roughly the number of cards multiplied by the number of cards, which we write as O(n squared, where n is the number of cards. The space complexity for storing the counts in our dictionary would be big O of n in the worst case, if all cards are unique. The key insight to optimize this problem lies in a fundamental mathematical concept, the Greatest Common Divisor, or GCD. If we can group all cards into groups of size x, it means that the count of every single card type must be perfectly divisible by x. This is true for card type A, card type B, card type C, and so on. If x divides all of them, then x must be a common divisor of all their counts. Think about it like this. If you have 6 red apples and 9 green apples, and you want to put them into bags so each bag has the same number of apples, and each bag contains only *1 color, you could put 3 red apples in each bag, 2 bags total, and 3 green apples in each bag, 3 bags total. Here, 3 is the common size x. Notice that 3 is the largest number that perfectly divides both 6 and 9. This largest common divisor is exactly what the GCD tells us. So our optimized approach starts the same way as the brute force. We first count how many times each card appears in our deck. We'll use a dictionary for this just like before. So, for our example deck 1, 2, 3, 4, 4, 3, 2, 1, our dictionary would show 1 has a count of 2, 2 has a count of 2, 3 has a count of 2, and 4 has a count of 2. Now here's where the GCD comes in. Instead of trying every x, we can find the greatest common divisor of * all the card counts. If we can find a group size x that works, then x must be a divisor of the GCD of all counts. And if the GCD itself is greater than or equal to 2, then that GCD value is our x. It's the largest possible x that would work. If the GCD is 1, it means the only common group size is 1, which the problem disallows. Let's walk through the optimized solution steps. First, we declare a dictionary to store the counts of each card. We iterate through each card in the input deck. If the card is already a key in our dictionary, we increment its associated count. If it's not, we add it to the dictionary with a count of 1. After this loop, our dictionary holds the frequency of every card. Next, we initialize a variable, let's call it g, to 0. This g will eventually hold the greatest common divisor of all our card counts. We then iterate through each key-value pair in our count dictionary. For each card's count, we calculate the GCD of our current g and this new card count. The GCD function is a standard mathematical operation. If g is currently 0, the GCD of 0 and any number n is simply n. So the first count we process will become the initial value of g. For subsequent counts, g will be updated to be the GCD of its current value and the new card count. After we've processed all the counts, g will hold the greatest common divisor of * all the card frequencies. Finally, we check if this g is greater than or equal to 2. If it is, it means we found a common group size of at least 2 that divides all card counts, so we return true. If g is 1 or 0, which shouldn't happen if there are cards, it means no such common group size of 2 or more exists, so we return false. This GCD approach vastly reduces the number of checks we need to do. Let's trace the optimized algorithm with our example deck. 1, 2, 3, 4, 4, 3, 2, 1. First, we declare a dictionary to store card counts. It's currently empty. We start iterating through the input deck. The first card is 1. Our dictionary does not contain 1, so we add 1 as a key with a count of 1. The dictionary is now 1, 1. Next card is 2. Dictionary does not contain 2, so we add 2 with a count of 1. Dictionary 1, 1, 2, 1. Next card is 3. Dictionary does not contain 3, so we add 3 with a count of 1. Dictionary 1, 1, 2, 1, 3, 1. Next card is 4. Dictionary does not contain 4, so we add 4 with a count of 1. Dictionary 1, 1, 2, 1, 3, 1, 4, 1. Next card is 4. Dictionary asterisk does contain 4, so we increment its count. The count for 4 becomes 2. Dictionary 1, 1, 2, 1, 3, 1, 4, 2. Next card is 3. Dictionary does contain 3, so we increment its count. The count for 3 becomes 2. Dictionary 1, 1, 2, 1, 3, 2, 4, 2. Next card is 2. Dictionary does contain 2, so we increment its count. The count for 2 becomes 2. Dictionary 1, 1, 2, 2, 3, 2, 4, 2. Finally, the last card is 1. Dictionary does contain 1, so we increment its count. The count for 1 becomes 2. Dictionary 1, 2, 2, 2, 3, 2, 4, 2. Now all cards have been processed. Our dictionary has the final counts. Next, we initialize our greatest common divisor variable, g, to 0. So g equals 0. We start iterating through the values counts in our dictionary. The first value we encounter is 2 from card 1. We calculate the GCD of g, which is 0, and this count, which is 2. The GCD of 0 and 2 is 2, so g is updated to 2. G equals 2. Next value is 2 from card 2. We calculate the GCD of g, which is 2, and this count, which is 2. The GCD of 2 and 2 is 2, so g remains 2. G equals 2. Next value is 2 from card 3. We calculate the GCD of g, which is 2, and this count, which is 2. The GCD of 2 and 2 is 2, so g remains 2. G equals 2. Finally, the last value is 2 from card 4. We calculate the GCD of g, which is 2, and this count, which is 2. The GCD of 2 and 2 is 2, so g remains 2. G equals 2. All counts have been processed. The final value of g is 2. Now we check if g is greater than or equal to 2. Since g is 2 and 2 is greater than or equal to 2, this condition is true. So the algorithm returns true. And there's our final result for the deck 1, 2, 3, 4, 4, 3, 2, 1. True. This is correct because we found that every card appeared exactly twice, meaning we could form groups of size x equals 2. You'll spot this greatest common divisor pattern whenever a problem asks you to find a common property, like a group size, that must simultaneously divide or apply to a collection of individual counts or quantities. Another strong signal is when you're looking for the asterisk largest such common property, or if the problem implies that such a property must exist for all asterisk elements. The time complexity of this optimized solution is O, n plus k log m, where n is the number of cards, k is the number of unique card types, and m is the maximum count of any single card. The space complexity is OK for storing the card counts. This GCD approach is a powerful tool. Try the next problem involving array counts and look for that pattern. If you found this helpful, hit that like button and subscribe for more DSA deep dives.